So this lesson is about the second derivative test, which will also help us to find local or relative maxes and mins. Now, we normally don't use this one. It's certainly not used as often as just your first derivative for max and min. But in a case where you might know specific information about a graph, this might be quicker and easier. And so here's what it says. It says if your first derivative at this particular point is equal to 0, which means that it's already a critical number. And if it's a critical number, then we know that it could be a possible max or a min. And then we know that the second derivative is greater than 0 or positive, which means that it's concave up. So critical number, concave up, we're going to have a local minimum. If the first derivative is equal to 0, so also same thing, critical number, and the second derivative is negative, so concave down, then we have a local maximum at that point. And that's it. It's pretty easy to use. Kind of a little confusing, I think. When you think minimum, you should think, we usually think first derivative is negative, or I don't know, minimum negative, maximum positive. But that's because the positive one is giving us concavity up, which would give us a minimum. And the negative one is giving concavity down, which would give us a maximum. So that's the only thing that sometimes people confuse a little bit. So here we go. We have critical values given at -1, 0, and 1. So they've already set the derivative equal to 0. They've gotten the critical numbers here. And here is the equation for the second derivative, and it wants us to determine if any of these critical values are maxes or mins. So we're just going to plug these values into our second derivative. So we're plugging in -1 and 0 and 1. And so we're going to have 4 minus 12 times -1 squared, 4 minus 12 times 0 squared, and 4 minus 12 times 1 squared. So it looks like we end up with -8. Just before, and this one is going to be the same as the first one, -8. So, according to our second derivative test, since this critical value gave us a negative number, then that means that we have a local maximum at x equals -1. Here we have a local minimum at x equals 4. We have positive, so minimum, and another negative, so another local max at x equals 1. And it's that easy. So let's go ahead and try the next one. This time our critical values from our first derivative are -2 and 2. We are given this equation for our second derivative, so we're going to plug those in to our second derivative. So we're going to have -2 squared minus 4 over -2 squared, and 2 squared minus 4 over 2 squared. And so we just work those out, and both of them are going to give us 4 minus 4 over 4, 4 minus 4 over 4, or 0 over 4, which is 0. And so that does not fit with our second derivative test. So this is not going to give us enough information. Now that does not mean that it's not a max or a min. It just means that we can't determine from the second derivative test whether or not there is a local max or min. So if the second derivative gives you a 0, it doesn't mean that it's not a max or min. It just means that we can't use that test to determine the max or the min. All right, on the back, we're kind of switching gears. This is another way that we can sketch our graphs without having to find quite as much information. If we know that a function is even or odd, then certain patterns are going to occur with that function. So that's what we're going to look at here. Now, we know lots of even parent function graphs like y equals x squared or y equals the absolute value of x. But for this purpose, I'm going to use y equals cosine of x. Remember, cosine starts up high, down, goes back up, completes a cycle in 2 pi units. And so this side is going to look the same. See if I can draw it fairly close to the same. All right. So obviously, it's an even function because it's symmetric to the y-axis. And so what we're going to talk about here is what's happening on either side. So values that are located the same distance away from the y-axis are going to be the same. Like the value at this point would be the same as the value at this point, or this low is going to be the same distance away as this low. And so on either side of the y-axis, the values are the same. As far as concavity goes, on either side of the y-axis, it's concave down, and then it switches to concave up. So concavity is also the same. For increase and decrease, we can see that here our graph is increasing, but on this side, it's decreasing. So these are actually opposite on either side of the y-axis. So for an even function, this is what happens. Now let's look at an odd function. So I'm going to use the sine, y equals sine x graph to talk about this symmetry. But we could have used any odd function graph. So a sine graph looks like that from 0 to 2 pi. Alright, so this one, of course, is symmetric to the origin. And if we look, points of the same distance away on this graph are opposite each other. If this one is positive, this one's going to be negative. So positive one here, negative one here. Concavity. When we look at the concavity, this is concave down on this side, concave up on this side. Concavity is also going to be opposite. For increase and decrease, though, when I look here, and remember, increase and decrease go left to right, so be careful with that. But if I look, this section is increasing, which on the opposite side of the y-axis would be this section, which is also increasing. Or if I go back over here, this section is decreasing. It matches up with this section, which is also decreasing. So increase and decrease would be the same. So this is what we're talking about. This is our function. Concavity is our second derivative. Increase and decrease is our first derivative. So points on either side of our y-axis, as far as the function itself goes, for an even function, they are the same. For our second derivative, concavity, they would be the same. But for increase and decrease, the first derivative, things would be opposite. And the same over here. This is our function, our second derivative, and our first derivative for an odd function. So using that information, we're going to fill out this little chart here. And if you'll look, the intervals here, 0 to 1, 0 to -1. So this is either side of our y-axis. This one is an odd function. Whatever the graph of this is odd. And so whatever this says for our value of the function is going to have to do with its symmetry. And so these are going to be opposite. So in this section it was positive, so in this section it would be negative. Here at 1 it was 2, so at -1 it would be -2. Where it's positive, negative. 0 is still 0, negative would be positive. For our first derivative, which is increase and decrease, it's going to be the same. So if it's positive from 0 to 1, it's positive from -1 to 0. And 0 would be 0, negative would stay the same, negative, and negative. And then for our second derivative, for an odd function, everything is opposite, so everything over here was negative. That means everything on this side, positive. So the next chart is for an even function graph, and so you may want to pause this for a minute and fill it out and then come back and check. So I'm going to go ahead and pause this and fill it out, and then you go ahead and pause, and then when you come back we'll have it all filled out and you can check. Alright, so for an even function graph, we're using this information. We know that the value of the function on either side of the y-axis will be the same. For concavity, which is our second derivative, it's going to be the same, but for the increase, decrease, which is our first derivative, things would be opposite. So here's what you should have in your charts. For our value, everything's the same, either side. For our first derivative, things are opposites. That's our increase, decrease, so positive, negative. Where it was positive, we were negative. And then for our second derivative, everything is the same again. So exactly the same as the left. So how this would help you, if you were trying to sketch a graph and you know that that function is even and you know half of the graph, then you don't have to find all the information on the other side. You could use this to help you with the increase and decrease and concavity for that particular function.